Good morning, guys. I've got my coffee and I am ready to talk science. So, this video is going to be a recap of chapter 16 of your science that you have read the past couple weeks. Now, I know that our book sometimes is hard to understand because it gives you all the details, it gives you all the specific words and vocabulary that pertains to this subject, but sometimes having all of that at once is a little overwhelming and hard to understand. So what I'm going to do in this video is just break down some of the main things that you guys need to know about atoms and their structure and how that works in the world, and the things that you will need to know for your test. Let's start with section 16A and discuss the development of the atomic model. Now, if you remember, a scientific model has to be workable. So in essence, even though these models were not complete, they did not contain all the information that we have today, they were still true in that they gave us some important information. And that's what science is. It's trying to learn more and more information. We'll never have it all, but we can continue to work and build on our ideas and understanding. So we find the idea of the atom being a tiny particle that makes up things in the world, dating all the way back to Hindu writings 2,000 years ago or more. We also find that the Greeks later were developing this theory and this understanding of an atom. Democritus, I'm not even sure if I can say that right, and Aristotle were both famous scientists that were trying to understand this idea of a particle that made things up. The thing that they had that was a restriction for them was that they believed that science could be understood with just your reasoning and your logic. And so they weren't big on doing experiments to try to understand. So they were limited on what they could discover about the atom. It wasn't until about the 1700s that we see that people were actually beginning to test and to understand a little bit more. It starts with John Dalton, and he had this same idea that the atom was indivisible. That means that was the smallest unit it could be. And he discovered the law of definite ratios. The law of definite ratios was that he understood there was a basis to each type of substance. So if you were to divide water, you would get oxygen and hydrogen every time, and that it was the same amount. Every time you divided a water molecule, you would get 1 oxygen and 2 hydrogens. So he began to understand that molecules were made of a base atom or a couple of base atoms. So that was the law of definite ratios. In the 1890s, J.J. Thomson developed his ideas a little further, but he realized that where John Dalton thought the atom was indivisible, that it was actually divisible. He found that the atoms were made of smaller particles and that they were electrically charged particles. He developed the plum pudding model, which we understand now is not completely correct, but he had this understanding that these molecules were moving around. And what he was seeing was actually the electrons moving, but at that time he didn't quite understand it. So he envisioned the atom as like a plum pudding that the molecules just kind of squished around in. In the 1900s, Ernest Rutherford developed the nuclear model, and he developed that by shooting particles through the gold film, and you've read that section, so I don't need to go through that. But by that experiment, he found that the atoms could pass through smaller things than what he was seeing of their size. And so what he was able to discover was that the atom had a nucleus and that the electrons was more of a field around it. And so those atoms could actually go through smaller things because their nucleus was all tied in the middle. So that disproved this plum pudding model of everything floating around and began to understand that there was a core, a nucleus. Okay, so you guys will need to know that, the nucleus, and be familiar with these names. Moving on, Niels Bohr was the next scientist who made significant advancements in our understanding of the atom, and he discovered that different elements give off different colors, and that was due to the different amount of electrons and how far away from the atom they got. So it was due to the size of the atom, the number of electrons, and when he was able to heat them, they emitted different light colors. And so that helps us to understand that the electrons were actually in a structure around, not just there, but they had different sizing and structures. So today we have what's called the quantum model, and that is a combination of all of these ideas and modern ideas from many, many physicists that have worked on this. And it includes the structure of the atom, the electron levels, the weights of the atoms, the chemical compounds that are made and how that works. And so for the rest of the chapter, it dives into that and helps us to have a basic understanding of the structure of the atom and how it works. Okay, so we start with the basics of the atom, which you guys already learned at the beginning of this year. Atoms are made of protons, neutrons, and electrons. And what we know about these is that protons emit one fundamental electrical charge. Now, we didn't use that term early on, but we are using that now, a fundamental electrical charge. And that's what the +1 E is for, electrical charge. So protons are one positive electrical charge. Neutrons do not have an electrical charge. They are neutral. That's the term neutron. And then our electrons have a negative fundamental electrical charge. So -1 E for each electron. Now, we also know that our protons and our neutrons are found in the nucleus of the atom, in the center. So those are called nucleons because they are the particles that are found in the nucleus. The electrons orbit around the nucleus. And here in a minute, we're going to talk about the structure because there's actually a specific way, specific orbits that they go around that nucleus. Each and every element is different, and it can be categorized by the number of protons that is found in the nucleus of that atom. Now, that amount of protons is given to us by the number, or the element's atomic number, which is found in the top left-hand corner of the box on the periodic table for that element. The atomic number gives us the number of protons, but it also gives us the number of electrons, since in an atom you would have the same number of protons as electrons. It also gives us the element's name and symbol. The symbols are used for chemical equations to write out the element without having to write the entire name. Now, below that you find the atomic mass. The atomic mass is an average number because inside the nucleus of an atom, there are protons and neutrons. Now, typically, there's the same number of neutrons as protons, but sometimes that number may be less or more. And so the mass is determined by adding the number of protons with the number of neutrons. And so the atomic mass found on the periodic table is an average of those elements of that type of atom. Your periodic table is found in the back of your book on page 518 and 519. And as you can see, every single element has its own number, its own atomic number. And that tells you how many electrons that atom has. Okay, so for this chapter, they are wanting you to focus on the first 4 energy levels. So we're going to turn here to my chart. Okay, the first 4 energy levels can contain 2 electrons on the first level, 8 electrons on the second level, 18 on the third level, and 32 on the fourth level. However, there is a pattern of filling the first 4 electrons. And you guys will learn more about this when you take chemistry farther along in high school. But for right now, just to have a basic understanding, we're going to go through and we're going to go through our first set of atoms so that you kind of get an idea of how this works. So our first atom is hydrogen, and it has 1 electron. So if we were to draw a hydrogen atom, all we would do is put 1 electron on energy level 1, sorry. Okay, our second Our second atom is helium. Helium has 2 electrons, because we know that by the little 2 up there in the corner. So if we were to make a helium atom, we would have 2 electrons, okay? Now that electron level is full, okay? And if you remember your chapter, it calls the outer filled, or not completely filled, but the outer level, energy level that has an electron is called the valence level, okay? So your valence energy level determines on whether your atom is stable or not. So helium is a stable atom, okay? Hydrogen, only having 1, is unstable. It compounds with other things because by itself, it's not got a full energy level. So you'll learn about that too as we discuss compounds further along. But for now, you just need to know that those are your valence electrons, the ones that are on your outermost level. All right, so if we were to look at the element 3 is lithium. And so we would go ahead and go to the outer level, and there's a lithium. Number 4 is beryllium, and you kind of draw them balanced, okay, just to help us to see it, okay? So that's beryllium. Element 5 is boron. Boron has another 1, okay? And 6 is carbon. So now we have 1, 2 on the innermost, and 1, 2, 3, 4. That's 6 electrons. That's carbon. If we were to have 7, that would be nitrogen. So we just start up here because this energy level can hold 8. So we're going to keep going. 8. 1, 2, 3, 4, 5, 6, 7. Okay, that's nitrogen. 7 is nitrogen. If we put 1 more, that makes it oxygen. Oxygen has 8 electrons. Okay, element number 9, and I'm just going through here. See, boron, carbon, nitrogen, oxygen. Number 9 is fluorine. Fluorine has 9 electrons, so we'd put another one there. Now we're still good because this level holds 8 electrons, and right now we have 2, 4, 6, 7 in that valence level, so we are still good. And neon then would have 10, making a full stable atom, neon. Okay, now it gets a little trickier when we go to this next level because our energy levels actually fill 2, 8, 8, 2 before it goes back and fills the rest of 3. It has to have those 2. And you probably saw that on the video I had you watch, and if it was a little confusing, that's why. Because this is how they fill, and this is how much they can hold ultimately. Okay, so let's go ahead and continue on. Element 11 is sodium, and it has 11 electrons, so we would then let's do it here. We're trying to even them out. There is sodium. Magnesium has 12, so we'll put that one there. Okay. Then it goes along, so I've got 11, 12. I have to go back to the other page for 13. Okay, so 13 is aluminum. We're going to have that there. Aluminum. 14 is silicon. So there's a silicon atom. Phosphorus is 15, sulfur is 16, chlorine is 17, and then our full level is argon, okay, and that's 18. 18 electrons. Okay, now at this point, we actually, even though it can hold 18, we've got 8, we're going to pop to this outer level, okay? So when we go to potassium, which has 19, we're going to be putting them here and here, okay? So 19 would be potassium, and then 20 is calcium, okay? Then you could go back in and start filling the rest of your 18 on this level, and then your 32 on that one. We're actually going to stop at 20 because that's as high as I want you to learn for now. 20 is calcium. This is how you do the energy levels for the first 20 elements on your periodic table. There are 3 different types of particles that are emitted from atoms when they become unstable or when they begin to decay. Those are alpha particles, beta particles, and gamma particles. And because of that, we have 3 types of decay, of nuclear decay. We have alpha decay, beta decay, and gamma decay, which is based on those particles that are involved in that process. The book first discusses gamma decay. Now, in gamma decay, you have your atom and you have your nucleus with your protons and your neutrons. Now, in this situation, the amount of energy within the nucleus has changed somehow, whether by an outside influence, conditions that the atom is under. And so the atom releases energy. So there's no change to the number of protons, there's no change to the number of neutrons, but it releases energy, changing the amount of energy found within that nucleus. That energy is released as gamma rays, and so it's called gamma decay. So if you remember gamma, it has no change of the nucleus, only a release of energy through gamma rays. The next type of decay discussed is the alpha decay. Alpha decay is called so because it emits an alpha particle. So when an atom undergoes alpha decay, it releases out of its nucleus 2 protons and 2 neutrons. Okay, so those 2 protons and 2 neutrons combine to form an alpha particle. Okay, notice that it does not have electrons, so this is just a positively charged molecule that is coming out of it. So it's an alpha ray, alpha particle. But this also changes the nucleus of our atom. So if our atom loses 2 protons, that's going to change its atomic number. It's going to drop it on our chart 2 elements, making it something different. So if you were to look on 518, where we were looking at our chart, and just say something like astatine, which is 85, when it underwent alpha decay, it would lower its number by 2, making it bismuth instead. So it's a different element that results. However, it is an isotope of that element because it'll still maintain the same number of electrons. So it will then become an unstable atom or an isotope of a different element. Okay, sorry that my drawings are not fantastic, but hopefully you can still understand. So the last one is beta decay, and beta decay happens after the alpha decay oftentimes because that isotope that is created is unstable. There is an off balance of protons and neutrons with the electrons. And so what happens in that case is one of the neutrons turns into a proton. Okay, so you've got a neutral that turns positive. So that counterbalances one of the electron charges. And then it also emits an electron. Okay, this is the beta ray or beta radiation that is emitted. Okay, but by doing this, it changes a neutron to a proton, so it's actually raising our atomic number. Again, changing what element this is. So when it underwent alpha decay, it lowered 2 atomic numbers, and therefore it was a different element. And now it's going up an atomic number because of gaining a new proton, and so now it is again a different element. The last thing that is important for you to understand is the idea of nuclear bombardment reactions. And that's basically the usage of nuclear energy, which is used a lot in our world today. So there are 2 ways that nuclear energy can be created, and that is through fission or fusion. Both of those do happen naturally in our world. However, physicists have learned how to prompt those reactions and be able to make use of that energy. So fission is when physicists actually force energy into an unstable atom, causing it to release particles, to break into smaller atoms, and it's a chain reaction, and so it'll break into smaller atoms, and as those break apart, they are releasing an energy. It's a very strong energy. It is what was used for the atomic bombs in World War II. Was the usage of fission. Now, fusion is similar. It's kind of the opposite of fission, and that's when physicists put energy in to fuse atoms together. So they may be 2 unstable atoms. They put the energy causing them to unite into one larger atom, and when that happens, energy again is released, and that energy is a very strong energy. It's actually stronger than fission, and it can also be used. Your book states that suns and stars get their energy from fusion reactions. So you can see that it's a very strong energy release. So that is the basics of these nuclear bombardment reactions and what you need to know. The test will be Thursday. And hopefully you guys, through this video and through looking back through your books, can kind of have a better understanding now of what this chapter is talking about. If you have any questions, please call me or message me so we can talk through it. And let me know if you need some help like that, because I'm here. I'm ready to help you with anything you need. You just gotta let me know. Go study, and we'll be taking our test soon, so I hope you all do good. Bye.